When we want to discuss the subject of current when it comes to electricity, the concept might actually be easy to understand or better to understand if we think about current in the context we might be more used to. We talk about current in rivers or streams and things like that, so we could imagine some sort of river with flowing water. It is that flow that we call the current. It's the same sort of thing here then with electricity, where the flow in the case of electricity is the flow of charge through some amount. So if I wanted to talk about, say, the current of water, there would be probably two things I would think of. That current I would expect to be proportional to how fast the water is going, and also how much water is going, as I might put in terms of either the mass of water or the volume of water. Mass probably makes the easiest amount of sense here, since we could imagine more or less dense water. So mass and velocity would be those things that I would expect to be the factors proportionate to how much stuff is going through. So I could put this into a sort of units that would say how much mass would be going through some region in a certain amount of time. So basically like amount of water per second sort of thing. So when it comes to current, as we use in electricity, that we're really talking about pretty much how much charge is going through in that amount of time. And we can put this into a differential form. So we talk about tiny little bits of water over tiny little bits of time, and that would then give us our current in terms of electricity. The same concept we could do with water. We can talk about how much water would be coming out of a garden hose in a second, and that sort of flow that we could refer to. And the same thing with rivers and the like. Also, in the context of water, we would also understand that sometimes there are things that would actually affect the flow of that water. No stream is usually, completely empty. There are often things in the way. For example, I could think of there being rapids in the way along the river. So any water that would try to get through would have to encounter those objects in the way. And what do you expect to happen? Well, you might think, well, the water is kind of like bouncing off the rocks. That would kind of prevent it from flowing forward. It would eventually go around, but that would end up slowing it down. So we could then talk of some idea of there being like a resistance to that flow, and that is the sort of resistance that we then could think of in terms of electricity again, that the material that the charge will try to flow through has some tendency to actually try to slow down that flow. Now that might be a little problematic, you might think, if I have something with a lot of resistance and I can't get much electrons or much electricity to flow through. But it may not be a total waste. There might be some utility to it as well. So another way to think about it is, what if instead I had a river? Imagine I had a waterfall. So if I have water falling down like that, you would expect it to change its velocity when it hits the ground. It's going to have picked up some sort of energy in that process. But I could also use this energy in certain ways. So for example, most hydroelectric power plants will use some sort of system of water falling, and then I have some sort of device down here that basically gets pushed by that water. In a sense then, basically I have the water doing work and I use it to some other sort of end. This is ultimately like how hydroelectric plants work. So at a dam, the water is ultimately falling down onto some turbine. The falling water pushes that turbine, and that's how we get energy out of that system. So there would basically be a couple of things that you'd expect then that would tell you just how much work you could possibly get out of this. One thing, or there's a few things really. There should be one is how much water is flowing. Second is how fast is the water going to hit, which should be proportional to how high up that water is falling. You can imagine the higher up it starts, then the greater it falls down, the more gravitational work is done at it, the faster it's going to go and hit the turbine and then push that around. And of course, thirdly, how much energy can I get out of that turbine, which could, be several factors that you might think of in an engineering context. But all of this we could try to translate over to the concepts that we have when it comes to electricity. So when it comes to the idea of the fall, that would actually fairly correspond well to, say, the change in potential. When you're falling, you have a change in potential energy, and it's that energy you're capturing. So if we talk about the potential difference from across that waterfall, or in this case, when it comes to some sort of resistor of sorts, then we can talk about that sort of energy that could be released from it from the flowing current. And in that case, it's also going to depend on what our current is. The more water we have, the more energy we can get out of that, so electric current should follow a very similar concept. So when it comes to the amount of power that I could potentially get out of such a thing, the two things that really should matter is the potential difference and how much stuff is going to have that sort of potential. So we actually find that the power in subsystem is the potential change divided by the current. Multiplied by the current. So current, more of it, we get more power. Greater potential change, more of the same. And if you want to look at the units, you should find that indeed this will give you units of power in watts. Now this is, of course, we might think the best case scenario, all the energy you could get out of that sort of waterfall system and getting it to do things. So the idea is then you want that sort of turbine that can try to take all of that energy and put it to some sort of work process. If the water is just falling down, well, that's not useful to anything you want to do. So the idea then is if I have some sort of resistor in my system here, in this case the turbine, or in the case of electricity, electrical resistance, it's somehow going to basically take all that current and take the energy out of it. So the way we're going to define resistance is that it's going to be based on the potential difference between before and after the resistor. Basically, it's saying how much energy is that going to be sucking up, and divided by the current. Why divided by? So this way we could talk about something being higher resistance in that a very small amount of current will get through only a very big potential difference, and that would then tell us we have really high resistance. It's really hard to get even this tiny little amount of current through, even when we have this big potential difference over it. So the higher the resistance, the more energy or potential difference you need to get even a little bit of current over. Conversely, if you had something that had very, very low resistance, then with almost no potential difference change, you could get a lot of current to flow through. That's the sort of idea then. Now that means we could rearrange that equation that referred to the power in some sort of circuit and replace it with our new definition of resistance here. And there's two different ways that we could do that. We could replace basically the voltage in this power equation, or we could replace the current in it. And the reason we might want to have two different versions in case we know one variable, not the other, but we could see with a little bit of replacement of things that either this could equal I squared R, again, solve for the value of the potential in this equation and then plug that in here. Or conversely, this can equal the potential difference squared divided by resistance. So if you want to think intuitively about this part of the equation here, this definition, it's basically saying that when you have a really big resistor that is going to be giving off a lot of power, even with a small current going through there, and of course have a lot of current going through even a small resistor, then you're going to have a lot of power, which kind of makes sense. It's basically saying, well, if this waterfall has a lot of water flowing over it, and we have a way of really stopping all that water, getting all the energy we possibly could out of it when it falls down that waterfall, then that would all go into the energy production that we want. So that's the sort of thing that we have happening here and what this equation is ultimately going to be telling us. So taking the analogy then ultimately from water current and applying this logic to the ideas of electricity, we can see what the basics are when it comes to any sort of circuit. One question you might ask, though, of course, is when we keep talking about this current, well, how fast are these charges going to be moving about? You might have been told that the speed of electricity is actually the speed of light. Well, the thing is, your book will actually show you a full demonstration, but you're going to find the velocity of your electrons in some sort of conductor to be on the order of 10 to the minus 4 meters per second. Okay, that looks a lot smaller than the speed of light, which is about 3 times 10 to the 8th meters per second. Okay, that's a little bit weird then, because at this pathetic speed, we're going, what, or a millimeter, less than a millimeter per second? That seems very, very slow, and yet that's how we're supposed to be sending our signals across the entire internet, how we're supposed to be transmitting all sorts of things. How does that make sense? Well, while the charges themselves may not move that quickly, there is something that does move at about light speed. And that is the electric field that we would produce when we turn on a circuit. It's not the case that we need the electrons to be moving around in the first place. The fact is, when we close the circuit, we've created an electric field in that wire, which then is going to push all those electrons around. So while the field that we create is ultimately going to be based on light speed, which we'll discover in later lectures, but it does mean that those electrons themselves aren't really moving around that fast. This actually also means something in particular when it comes to how a circuit works in your computer, in particular the ones that are the microchips doing all the processing. So your CPU in your computer, it's trying to use a bunch of logic gates and using electrons to basically move around. That means that any computer is really based on this sort of speed. Now, if you could somehow have your processing bits not go at the speed of these electrons, but say light speed, or at least something pretty fast, well, it sounds like you could do a whole lot better. And that's a very difficult thing to get going, but it's something being currently researched because it's pretty easy to look and say, okay, this puts significant limitations on how fast you can process. It also is the reason you can make a chip only so large, because if you make it larger and larger, then the time difference it takes to get across that chip will make a difference when you're doing calculations. So even from a computer science stand, this is an interesting limitation which future people may find a way of getting around, but it's because we're ultimately not using electricity in the way we're used to. Either we would be using something in a quantum mechanical way that has very interesting properties, or you might have even heard of a photon-based computer. So the stuff's going around at light speed, and that's the fastest you can get. You can see going from here to here would be a nice improvement. But in the meantime, your electricity in the wall and anything else is ultimately based on this, though the electric field will go at about light speed.